All right, so we have a problem here, cogeneration plant, and we're given quite a lot of information about all the states and everything. What I've done here is I've just tried to color coded it where the steam splits. So the problem tells us that 45% of the steam is extracted at 500 kilopascals. So right here at state 2, Y is equal to 45% or 0.45. So it's something that's given us. Um, all along the black line, so M dot 1, kind of tracing it back, 7, 6, those are all the same mass flow rates. Um, and along the blue line, M dot G, 4, all of those are the same, 5, those are the same. Write that as well. So dot 3, dot 4, dot 5, those are all the same. It's just a fraction of that full mass flow rate. Yeah. And then our red line here, we're along that guy, that's constant mass flow rate. So M dot 2, let's see, down here is M dot 8. That's it. So M dot 2, dot 8, that's a fraction of the total dot. And in fact, that's one thing we're supposed to find. So we'll kind of keep that in the back of our mind. Let's also look at the Q dots and make sure we've got a handle on those. So of course we've got a Q dot in for steam generator, but we also have another Q dot over here. So at the very bottom, why it's a cogeneration process or cogeneration plant, because not only are we producing power, but we're also using some of the heat that's extracted from this system for some other process. So that's the information we're given down at the bottom, the Q dot process. And that Q dot process is actually what we're going to use to figure out mass flow rate of our of our steam M dot going into that first turbine stage. So the full mass flow rate, right? I'm looking for this guy up here. So the way I'm going to calculate that is I'm going to look at my Q dot process and I'm going to do an energy balance on that heat exchanger down there. So it's going out of that box. So it's going to be the sum of the things coming in at 8. Oops. This guy, some of the M dot H's going out. So going in, I've got things going in at 2, and then they're exiting at 8. So I have dot 2, M dot 8, H8. But of course, I know that M dot 2 and M dot 8, they're both exactly the same, and they are equal to Y times M dot, it's H2, it's H8. Here we go. And so now I can get my first governing equation. So the mass flow rate of the steam M dot is just going to be Q dot of the process, which I'm given to be 5, 10 to the 8. It's kilojoules per hour. It looks like I need things in seconds, so kind of keep that in mind. So 1 hour, 3,600 seconds. Perfect. Bottom, I'm going to have Y, that there, and then it's H8. So I need Y and I need H2 and H8. Oh, actually, I don't need Y because that was something that was given to me. Okay. And then I need the net power developed by the cycle. Let's see. So my net power developed by the cycle is going to be the power output by the turbine minus the power input that's required by pump 1 and 2. It's going to calculate that. So my W dot out is going to be M dot. Let's see, H1. Uh, I'll kind of lose the color coding, I think. Y, H2, S1, Y. There's the power output by the turbine, and of course we need for each of the pumps. So pump 1 is a fraction. It's going to be 1 minus Y, and it's H5, it's H4, minus the other pump work. So for pump 2, and that's between 7 and 6, and so this is going to be sorry, y'all. Let's see. All right. And then it'll be between 6 and 7. So it's going to H7 minus H6. And so the only thing that I need to get at this point, H values. So I've got my saturated tables for water down here, and my superheated table. So let's see. I'll just kind of continue to go back and forth. Hopefully, be too annoying. But state 1, I have P1 H values. So it's going to be the enthalpy at 6 megapascal, 60 bar, temperature of 500 Celsius. It is superheated. So go to my superheated. So you'll figure that out pretty quickly. But I've got an enthalpy of 3517. So you could see I've also got to get my entropy value because that's maybe I'll put it up. Yeah, that's okay. I'll leave it the way it is. So this guy right here. All right, so this is going to be 6, sorry, 6. It's going to be 7 per kilo. 3157 kilojoules per kilogram. Okay. All right. And then of course I need to get my S1 value. So this guy is 6.99. How many nines? 4 nines kilojoules. I realized that I put a kilojoules per kilogram K on the enthalpy, and that definitely doesn't need to be there. So, all right. All right, so state 2. So the information that I'm given about state 2, oh, this is kind of interesting. So I do have an isentropic efficiency that I have to worry about, and this is a little bit annoying, but that's okay. We haven't done one of these yet, so at least you get to see how it would work. Very unlikely I'm going to make you go through this process on a test because it requires it's a lot of little tedious work, but at least you could see how it's done. So at state 2, I know that there's an isentropic efficiency for this first stage of 82%, and then my pressure is 500 kilopascals. So let's at least write that down. There we go. So my H2S, because that's what I need to get first. I need to get 2S. So H2S is going to be at a P2 of 5 bar. S2S, that's the same as S1, so 6.9, another 9 kilojoules per kilogram K. And so at this phase, it turns out we're superheated. So I'm going to go to my superheated tables. So let's see, hopefully anyway. All right, so 5 bar, going to have to interpolate. So at 5 bar, an entropy of 6.9999 kilojoules per kilogram K. You're going to have to interpolate. So I've got a value of 2827.9. That looks okay. So 2827.9. 8.7 kilojoules per kilogram, and that's it. And then we need to figure out state 2. So for this guy, we're using our isentropic efficiency for the turbine, and we'll apply that to the first stage of that turbine. So it's going to be H1 SH2 over H1 H2S. And so I've got H1, I've got H2S. It's just a matter of figuring out H2. So my H2 ends up being 2951.9. So now we got that. In fact, I think I want to highlight things as I get them, so happy about it. So I got that guy, got state 2, I'm all good there. And now I need state 3. So let's see. So state 3 is over here at the outlet of the second guy. And so what I'm going to need to do is I know ideally S2S or S3S and S2 would be the same. So H3S, they give us the pressure. P3 was 60 kilopascals or 0.6 bar. But our S3S, it would be the same as what S2 is. Okay. So let's kind of go back up here. So S2, the properties that I know about that, it's going to be at 5 bar. But now it's going to be at that enthalpy that I solved for, H2, being equal to 2951.9 kilojoules per kilogram. So it is slightly annoying. So let's go see at 5 bar, that's on there actually. 5 bar, is it 2051? Shoot. Okay, hold on a minute. Let's see. I'll have to pull up those tables. Okay, so we got it. Sorry about that. All right, so if you recall, we're looking at 5 bar and an enthalpy of, what was it, 2951.9 kilojoules per kilogram. And we need to get the corresponding S value. So the corresponding S value here, 7.25 and change. So this is 7.25 0.32. And the reason that that's important is because we need it up here. So let's back up here. So this was again 7.2532 kilojoules per kilogram. Okay. And that's what we need at state 3S, right? So this was 7.2532 kilojoules per kilogram K. All right. And so now let's go to our saturated tables. Hopefully we have those there. So let's see. Okay, good. So here we are. So our at 0.6 bar, our entropy was 7.25 and change. And so you can see that that's going to be between our S sub F and S sub FG. And so I just need to, I know that at state 3S, I know that it's saturated. So let's put that. I know this is saturated. H sub F plus our quality times H sub FG. I do have an H sub FG value. And of course, my quality here can be found from my entropy value. So for an isentropic process, this is going to be S at state 3S minus S sub F over S sub G minus S sub F. And so, of course, those values can be found. This is your S sub F and S sub F, S sub F and S sub G. So I can at least plug that stuff in. See that? So this is going to be 7.2532 minus S sub F. I need to see it. 1.1453. So 1.1453. 1453. Oops. S sub G 7.532. Right. 532. Yeah. So for your quality at the end of that isentropic process, I've got 0.9563. And we're going to plug it up, of course, in here. So it's the H sub F. Where's he? H sub F 359.86. Plus 0.9563 times my H sub FG, which is 2293.6. Yeah. And of course, all of this is kilojoules per kilogram. Yeah, it's a lot of work to get state 3S. This is why I wouldn't do this on to you on a test, giving you an isentropic efficiency that you had to deal with to get, your new S2 value that's not the same as S1. But, at least a good thing to see how it's done. But I've got 2553.2. 2553.2. Okay. And then of course we can use our isentropic efficiency again. So this is going to be H2 minus H3 over H2 minus H3S. We've got our isentropic efficiency of, what was it again? 0.82. Yeah. 0.82. And so now we've got a H3 value, 2625. 0.2, I think. Sorry, 20. Nope, that's it. 2625. All right. So that was a lot of work to get that, wasn't it? There's our H3. See what else we need to get. I know that some of these things are given to us. So I just want to kind of like go through and highlight what I've got so I know so far. So I've got state 1, I've got state 2, I've got state 3. It looks like these state 7 is given to me. State 8 is given to me, so that's actually really nice. Okay, so I need 4, 6, and 7. That shouldn't be so bad. All right, so it looks like 4 is a saturated liquid at 0.6 bar. So that should be easy enough to deal with. It's not 3. And it's going into a pump, so I probably how I got state 4. H4 is going to be going into a pump. Saturated liquid at 0.6 bar. So that's in our saturated tables, and go 359.86. And then because we're going into that pump, I'm going to go ahead and get our specific volume as well. So it's this guy right here, the number that's already been multiplied by 1,000, so 0.001 and change. So 0.0010331, and it's meters cubed per kilogram. Okay. I'm going to highlight at least this guy, so feel good about that. State 5, looks like state 5, I've got a pump, right? And the pump has an isentropic efficiency of 88%. Of course it does. That's okay. So 5S, state 5, I'll put over here. So isentropic pump work is VDP 5 minus P 0.001031 liters per kilogram. Mentioned it before, but if you put your units in kilopascals, your units will be happy. Got 450 kilopascals minus 60. Go. And this will give you units of kilojoules per kilogram. Doesn't really matter what we get there because we just H5. So I know H5 minus H4 is pump work. Sorry. Isentropic efficiency for our pump. 88. So it's isentropic pump work over real work, which is H5 minus H4. So I've got an H5 value of 360. Go. All right. So H5. All right, that feel like we need one more and that's it. So now we've got 4, 5. Very last thing is this state 6. And at state 6, do have, like, I know it's going into a pump. Um, so okay, but I I have some other information that actually tells me a little bit more about the state, or something else that would allow me to actually calculate what that H6 is. So we can actually calculate him correctly by doing an energy balance on this little section right here. So I'm actually going to do it on the picture so I can see what I'm doing. So I would have the sum of the m dot h's going into this little spot right here. So that would be m dot 5, h5 plus dot 8 dot 6 h6. And then I might want to put that of y's and 1 minus. So m dot 5 divided by m dot is going to be minus y. M dot 8, dot 8 is on the red line. So m dot 8 divided by m dot is y. And m dot 6 divided by m dot, oops, is just 1, 6. So we can, since we know y is 0.45 because that was given to us, know all our other h values, I can actually just calculate what h6 is here. So correctly. I've got 4, 2, there we go. All right. So I think at this point, I have everything that I need to plug into my governing down here. So for MDOT, that I end up getting 130.6 per second. And I kind of ran out of room here. So my W dot net out, that being, you'll calculate it in kilopascal. I'm sorry, not kilopascals, but kilowatts. You need to put it in megawatts. I've got 96.8 megawatts here. So there's second. All right, so we'll move on to second one. All right. So let's see. We have second. All right, so we've got a combined heat and power system providing turbine power, process steam, and steam for a factory space heating load. So let's just kind of see what we've got. So, oh, here we are. So they don't actually draw the little arrows for us, but that's okay. We can draw arrows. So they tell us, oh, yeah. So it says it provides turbine power. Guess I can draw that. That's, if I, all of these together, this is going to be a W dot out. And this is for all 3 of the turbines. I'm just going to draw one thing. About that. We have process steam. That's going to be going somewhere, but it's a Q dot out. We'll call it Q dot process because not feeling very creative at the moment. And then we've got a Q dot, so we've got a heating load. So there's a process steam and there's a heating load. So I'm just going to call this Q dot load. Perfect. Okay. We also have a condenser here, so there's going to be some Q dot out here. Yes, and then there's a steam generator, the Q dot in. Got some pumps here. There's a pump. So here's a W dot in. Here's a W dot in. And I think just, yeah, I think for time's sake, probably we'll just worry about governing equations again. I'll give you the final answers that I get if you want to look up those. Well, I don't know, should we? Let's get our governing equations and see how much time we have. All right, so we've got, it's like what they give us. They give us enough information to, they give us enough information. They give us m dot, and then they give us enough information to get the H values at state 1, 2, 3, 4. Looks like all throughout it. They also give us the fraction of steam that comes off of that first high pressure turbine, but they don't give us Y prime. I'm sorry, not Y, but Y prime. So this is a question mark. I don't know him. Yeah. I think let's do that. Yeah, let's make this a governing equation problem. So let's say I know m dot 1, I know all H values, and oh, Y. But I don't know the Y prime, and so I don't know that Y minus 1 minus Y minus Y prime. And so I need to get I need to get my governing equation for all my stuff. So the rate that the steam is extracted as process steam, let's go ahead and get that. So the process steam, well, that one's not that bad. If I know all the H values, sorry, if I know all of the H values, this is just going to be the sum of the things coming in minus the sum of the things going out. So I have in minus out. And it's going to be a fraction of everything, right? This is going to be m dot times y. It's h2, it's h1. And presumably I have all of those values. In fact, I'm going to go ahead and just values right now, okay? So let's see. I'll highlight it too. So H1 1302.5 per pound mass. Oops. So now if you're watching this, it's like fast forward, pause and stuff. H2 1184 point. Hopefully maybe this'll be useful if Some practice getting values. 3, that being 1083.2. I realize I put kilojoules per kilogram on the fix that right now. Yeah. Yeah. All right, I'm gonna pause this while I just write down the rest of them so you're not waiting on me. Okay, so there you go. All right, so there's all of our H values. That's the tedious part. So I would say it would be worth probably like I mentioned, the isentropic efficiency for your turbines. Um, on a test, very unlikely if you have multiple stages of expansion, those isentropic efficiencies for the first turbines are going to be 1. Just because it means that you need to go back and calculate an entropy value for the outlet or for the inlet of the last turbine, and it becomes kind of a pain, as you saw in the last problem. So I could say that this is isentropic efficiency of 1, both of those, and this one's a different isentropic efficiency. That would be something that I might do on exam. The other thing that I would encourage you to do is make sure that you can make the units work out when you calculate pump work with English units. Um, you know, got to make sure that like the VDP equation is going to end up giving things in BT per pound mass. So just be cognizant of that. All right. So we've got our Q dot process. We're given M dot. We were given Y. We were given H2 and H1. Let's see what else we need to get. So dot the Q rates of the steam that's extracted as a steam process, and then we need to get rate heat transfer for the process steam and heating load. Oh, we got that. Oh, I see. I'm sorry. I misread the last question. So what part A is actually asking dot 2. And B is it's asking about the rate that steam is extracted. So it's asking for the mass flow rate of that steam going into process. So, I mean, that's easy enough. M dot 2 is just Y times M dot 1, and we were given both of those things. And then the rate of heat transfer for the process steam. So that's this guy. And then, of course, I guess we have to get the heating load as well. So this guy isn't so bad. Heating load, Q dot L, going to be M dot times Y prime. It's the inlets minus the outlets. So H3 minus H9. I do need to figure out that Y prime, and probably our open feed water heater at the bottom there is a place to do that. So if I did my mass balance on that guy, let's kind of zoom in here just a bit. So it's 10, that's 100% of the flow. 8, it's Y. 9, this is 9, and 9 was the Y prime. This is 6, and that's 1 minus. And so if we did our energy balance on that, we're going to get some of the stuff going in, and I'm going to go ahead and divide by m dot so that I have y plus y prime plus and minus y prime 8, 6. And then all of this is going to be h10. And if we have all of those h values, we've got y, right? So let me go through here. I've got this, and this, and this. I've got everything except the y prime. So I just need to solve for y prime. Let's see. I have 7, 6, 3. So m dot 2, that being pound, pound mass per hour. For here, q dot process steam dot load. I've got 545 billion per hour. At 451. So we did the net power developed, right? So let's get a governing of that. Might be a long one. So for our turbine, we've got things going in at 1, things leaving at 2, 3, 4. At everything. So it's m dot times h1 y h2 y prime h minus minus y prime h4. And then we've got our 2 pumps. So pump 1 is between 5 and 6, and that's a fraction of the steam. So 1 minus y prime, 6 minus h5. And then the second pump, that's the full mass flow rate, and that's 11 minus 10. 11 minus h. And if you want a number for that, I do have one. 2.252 T. All right, so hopefully that is helpful. Know if you have any questions. All right, good luck studying.